Hey, welcome back. Our next speaker this morning is Wanlin Li from Washington University. She will talk about Abelian varieties of prescribed order over finite fields.
Thanks for the introduction. It's my great pleasure to be here for Andrew. As some of you may know, I just moved away from Montreal like 2 months ago to Washington University in St. Louis, not in the state of Washington, not in Seattle, in St. Louis, Missouri. And since I was here recently, I can provide a very recent story of Andrew. So recently, Andrew invited a visitor over to discuss math with us. And actually, due to the circumstance, I actually didn't get to meet with Andrew in person very much. So I was very nervous about discussing math with him in person in his office. And I also have the common problem of mathematicians, which is lack of confidence. So I would say things like, the curve C has genus 2, right? Hoping to get some reassurance from the audience. And after half an hour or so, Andrew said, Wanlin, do you know you're very intimidating because you keep on quizzing people? So yeah, that's my recent Andrew story. I feel if Andrew found me intimidating, then that's something. Okay, so today I want to discuss a project that I did during my time in Montreal. And it was joint work with Raymond van Bommel, Edgar Costa, Bjorn, Poonen, and Alexander Smith. And I'm very happy to speak after Ken, who had already been discussing the order of elliptic curves and Abelian varieties over finite fields. In his talk, he was having a global object and reducing mod P and discuss the distribution. In my talk, I will be mainly focused on finite fields. So we'll be discussing Abelian varieties of prescribed order over finite fields. So when we talk about Abelian variety, we always start with elliptic curves. As we've already seen in Ken's talk, that given elliptic curve defined over finite field FQ, we know from the Hasse bound that its order is the number of FQ points on E is between Q minus 2 squared to Q plus 1 and Q plus 2 squared to Q plus 1. And moreover, for any fixed Q, we know exactly which integers does show up as an order of an elliptic curve over FQ. Okay, and in particular, when Q is prime, actually all of the integers in this interval occur as the order of an elliptic curve. Then it's very natural to ask the generalization for Abelian varieties. If I have an Abelian variety of dimension n defined over a finite field, again, the Hasse Weil bound tells you that there's an upper bound and lower bound for its order. And it's exactly its upper bound and lower bound, as you can see, is exactly the nth power of that order for elliptic curve. And then it's very natural to ask that if I fix my finite field of Q, I fix my dimension, right? Then what integers actually do show up as an order? And what is the maximal subinterval inside this allowed Hasse Weil interval that shows up as orders for Abelian varieties of this fixed dimension? And in particular, one can even ask a more refined question. What if I'm interested in certain interesting families of Abelian varieties? I require my Abelian variety to be ordinary or having a certain P rank. Or if I, instead of thinking about products with curves, right? If I only allow simple Abelian varieties or geometrically simple Abelian varieties, and what if I want my Abelian variety to be principally polarized? So this is the question we are trying to start in. And here's our main theorem. So first of all, let's fix my finite field FQ. And for any sufficiently large integer n, we were able to show that every integer in the following interval shows up as the order of an Abelian variety A defined over FQ of dimension n. And you can impose all of these conditions you want. And as you can see, this interval actually doesn't differ from, well, if you take the nth root, it's not that different from the Hasse Weil interval, right? Of course, because you're taking the nth power, it's infinitely different, I guess. And this theorem is, in practice, like our method is effective, even though we didn't work out the exact effective version in this strong form. But I will show you a consequence of a slightly weaker version of an effective version. Okay, and then another thing we did is when we study objects or finite fields and doing such statistics, there's always two directions people go. One direction is the large n limit, as dimension or as genus the curve goes, right? Then the other dimension is large Q limit. So we also think like if I fix my dimension n and let Q go to infinity so that we'll have more and more Abelian varieties over Q because the field is getting larger, then what's the largest interval where every integer shows up as the order of abelian variety of n-dimensional abelian variety is given by the following form. So the point is, what's interesting here is the leading term is q to the n. That's fixed because it's an n-dimensional variety essentially. And then the interesting thing is the constant in the q to the n minus a half term. And what we proved was that as q goes to infinity, this value converge to this given lambda. So next, let me show you a consequence of effective version of our first theorem. And the first theorem will be the one I'll be focusing on today. And also I'll tell you the motivation for our work. So the motivation is that if I ignore the dimension of the abelian variety, just give you a finite field of q and ask which integers it shows up as the order of abelian variety over this field, doesn't care about dimension at all, right? Then it's the same as, let's consider the union of the Hasse Weil intervals, union given by n. As you can see, because these intervals are pretty big, they very soon overlap. So for q being 2, 3, 4, 5, every positive integer lies in this union. And for q greater or equal to 7, all but finitely many lies in this union, right? And in last year in March, Howe and Kedlaya posted this paper on arXiv saying that every positive integer is the order of an abelian variety defined over F2. And we found this result very interesting and decided to see if what happens for other fields. That's our motivation, really. So we were able to actually prove that it's true for q equals to 2, 3, 4, 5. Every that's allowed by the Hasse Weil bound. Every positive integer does show up as the order of abelian variety defined over this fixed small field. And also for any given q, every integer that's at least q to the 3 times square root of q log q is the order of abelian variety over that field. And also this bound is optimal except the constant 3 that we didn't try very hard to optimize, but this order is optimal. And this is a corollary really to our main theorem, but we made it effective. Okay, so these are the results, and let's talk about how to deduce such results and how to start how do I start the abelian varieties or finite fields with a given number of points, right? Okay, so given abelian variety defined over a finite field, its most important invariant, I would say, is the characteristic polynomial Frobenius acting on the L-addict module of the abelian variety. And if this variety, for example, is a Jacobian of a curve defined over a finite field, this is essentially the numerator of its zeta function, right? But we normalize it in such a way that it's a monic polynomial. So which is different from the Euro normalization you see from the zeta function perspective. And if an integral polynomial shows up this way, is a characteristic polynomial for some abelian variety, and in this talk, I will call it a Weil polynomial. And the term Weil polynomial is not a well-defined term. It can be used for different concepts. And actually, in our paper, when we say Weil polynomial, this is not what we meant. But in this talk, when I say a polynomial, the Weil polynomial, it means it comes from abelian variety. The reason this is the most important invariant for abelian variety is because Honda-Tate theory tells us that it exactly determines, this is one-to-one correspondence, this polynomial, to the isogeny class of this abelian variety over FQ. So it determines the isogeny class. And also there are many arithmetic invariants of the abelian variety that can be read off from this characteristic polynomial. And for example, it's one we care about, the number of FQ points, right? So the order of A is simply given by evaluating the characteristic polynomial at 1. So this means that if I want to show you the existence of abelian variety with a certain number of points, it's the same as I give you a polynomial, I prove to you it's a Weil polynomial, and when I evaluate that one, it gives me that number, right? So we want to turn this problem from constructing this geometric object into construct certain polynomials satisfying some conditions, right? So as I said, like this polynomial determines the isogeny class, which means that there are other informations about the abelian variety that you can extract from this polynomial. And for example, one proposition, one lemma we proved is that for any fixed q, you can always get a integer L, which is bounded by some power q, such that if I know the Weil polynomial modulo this integer L for some wave polynomial, I can assert from this information mod L, I can assert that my abelian variety has the desired properties that I want. For example, the ordinary, geometrically simple, and isogynous to a principally polarized one. So this isogeny class contains a principally polarized object. And the important thing here is that this constant L, as you can see, only depends on Q. It does not depend on dimension of the abelian variety. Okay. So this gives you a way to determine these properties by looking at the reduction of the polynomial. Okay, so now we can discuss what kind of polynomials are the ones we want, right? Again, it just follows from Honda-Tate theory. It says that a monic degree 2n polynomial with integer coefficients is a wave polynomial if it satisfies the following condition. So first of all, f need to be, we call it Q-symmetric, which means that all of its roots shows up in pairs. So the multiplicity of a root alpha has to equal to the multiplicity of the root Q over alpha. This comes from the duality in etocal homology. And also then all the complex roots of f must have absolute value square root of Q, because these roots are the Frobenius eigenvalues, right, of the Frobenius operator on L-adic Tate module. And then there is in general, there is a p-adic condition, which essentially says that Newton polygon has to break in integral coordinates. But we can restrict to a simpler case, which is if I only think about ordinary abelian varieties. Ordinary abelian variety means that my middle coefficient of the wave polynomial is not divisible by p. And in this case, and if you ask your polynomial has the middle coefficient to not be divisible by p, then conversely, the p-adic condition is automatically satisfied. So this is the if and only if for ordinary abelian varieties. Okay, so this means that if I want to construct a polynomial, if you give me a polynomial and I want to show that it's a wave polynomial for some abelian variety, all I need to check are these conditions, right? Okay, so then naturally, the next question is, I want to construct some wave polynomial with a prescribed value at 1. So let's discuss how do I construct wave polynomials? What do wave polynomials look like? Well, so first of all, I want to be Q-symmetric, right? And for the Q-symmetric, there's this trick, which is essentially I take any polynomial and Q-symmetrize it in some sense, right? So we define this hat operator, where when the input is just any polynomial, and then the output will be Q-symmetric. So I put in a polynomial of degree less than 2n. So when I do this operator, I need to give you an n to begin a target degree to get, yes, thanks for the question. So the reason is if I get rid of ordinary, then the p-adic condition will be much more complicated to state in general. And since the problem we care about, we just care about whether there exist abelian varieties with the prescribed order, and it's already enough to do ordinary ones for most of the case. Yes, exactly. Right. And you can construct non-ordinary ones you can construct it with, like, for example, I just want my P rank to be G-1. You can do that. But ordinary for our purpose was already enough. Yeah. It makes the p-adic condition much easier to state. Yeah. Okay. So yeah, we have this process that if I take in a polynomial of bounded degree less than 2n, then my output is a degree exactly 2n polynomial that's Q-symmetric. And one thing to note is that the leading coefficient of the h hat will be the constant term of h. So what we'll do is h hat will be our targeting wave polynomial, and I want it to be a monic integral polynomial of degree 2n, right? So what we'll do is, so that's why I will usually pick my h to have constant term 1, so that the leading coefficient for h hat will be 1. So this is how we guarantee the Q-symmetric. And moreover, the relation between the coefficient on degree n between h and a hat is simply multiplication by 2. So the coefficient for actually n in h hat is just twice of that for h of n. So this also tells me that by controlling h, I'm able to make sure that h hat satisfies the condition C. Okay, so what I'm proposing here is that I can give you any polynomial h, and by restricting certain properties of h, I can guarantee my h hat to satisfy conditions A and C. So now let's talk about how do I achieve B. So meaning that I want my h hat to have all complex roots being exactly absolute value square root of Q. So this is a very cute winding number argument. And here, this is the proof in my talk. So, okay, let's take a small disk with radius 1 over square root of q. Okay, it's blue disk here. And the lemma says that if my h does not vanish for any complex value inside my small blue disk, then when I do this h hat operation, all of it is a degree 2n polynomial where all of its roots will exactly have an absolute value square root of q. Now here's the argument. The argument is, okay, so my small disk D, my small blue disk, after I map it by h, as you can see, because h does not vanish, it maps to somewhere, does not intersect the origin, does not include the origin. So the winding number of h of D is 0, right? And so if I define this polynomial g of x, which is x to the n times h of 1 over x, and evaluate on the orange circle, which is the circle with radius square root of q, then its winding number is n coming from the x to the n, right? Because h of 1 over x evaluated on the orange circle does not vanish. So g of x, g of this curve c has exactly winding number n. Okay. Now I project down my orange curve to the real axis. Okay, take the real part. Project down to the real part. So since the winding number was n, it had project down to the real part. It has to cross the 0 2n times, right? Because I went around n times. So if I project down to the real part, it has to cross at least 2n times, right? But then when I take the real part and multiply by x to the n, this is exactly my h hat. So this means that if I evaluate my h hat on the circle with radius square root of q, it has at least 2n roots. But my h of hat is a polynomial degree 2n, so all of its 2n roots has to be lies on this orange circle. And that's the argument. Okay, so what we have established so far is a way to construct polynomials such that it's q-symmetric and all of its roots exactly have complex roots have exactly absolute value square root of q. Okay, so now we are ready to construct wave polynomials with prescribed value at 1. Okay, so we actually have two methods. So let's start with the first one, which is the easier one. I want to construct certain polynomials, right? Let's start with power series and then truncate to get a polynomial. And this allows us to prove a slightly weaker version of our theorem. So namely, let's prove that every sufficiently large integer is the order of Abelian variety for some ordinary Abelian variety over Q. So this means that translating to the constructing polynomial language is that given a sufficiently large integer m, I'm going to produce you a target dimension n and a integral polynomial h such that when I do this hat operation, evaluate 1, I get exactly m, right? And also my h does not vanish in the complex disk, right? And also, I guess the last condition is I'm going to require that the coefficient for h hat is not divisible by p, which is you just need to adjust a little bit. Okay, so how do we do it? Well, the reason you start with power series is because power series are complete, right? You want to hit a particular integer, and if I consider power series whose coefficients are in a bounded range, let's say a coefficient is exactly from 0 to q, right? What I can do is I take this integer m, take its q-adic expansion. This will give me in this way I can construct exactly a power series such that I can, when I evaluate at 1 over q, I get the targeting integer, right? Because it's complete. So I know like the range of its value it could hit, then anything in between I can hit it. And that's which is different from integer polynomial that's discrete. So the point is, as you can see, I want h hat 1 to be m. And h hat 1 has two components. One part is h of 1. The other part is q to the n times h of 1 over q. So I'll tell you that the main term will be q to the n times h of 1 over q. So what we'll do is we'll construct a power series such that q to the n times this power series evaluated 1 over q exactly gives me m. Okay, and I'll ask this power series have always coefficients in integers. That's step 1. And then step 2 is I will truncate at degree n to get a integral polynomial h. And so after I truncate, right? If I take this h hat evaluate 1, it probably will be a little bit off from m by a little bit. So what we'll do is we add a multiple of x to the n to make sure that my h hat 1 exactly equals to m. Do a small adjustment here. And then the step 4 is check whether the coefficient for the middle coefficient of h hat for x to the n is divisible by p or not. And if it is, let's just adjust it a little bit again, and also simultaneously adjust the coefficient next to it to make sure when I evaluate at 1, that value didn't change. But now my coefficient for x to the n is not divisible by p anymore. So we do this to guarantee the ordinary. And then the last step is to prove that, to make sure my polynomial h does not vanish on the disk D. And this can be done very explicitly. Like I even have an example of like given m equals to 1, 2, 3, 4, 5, 6, for example, over F3, I can explicitly construct you that h and h hat, where h hat is a wave polynomial, and when you evaluate the 1, you get exactly the targeting number you get. So it's very, very effective method. So yeah, which I said the advantage of this method is very simple, and it's very easy to make an effective bound on how large m need to be. And also, as you can see in this method, that if I fix my dimension n, I can also deduce what's the interval I get for any given fixed dimension. Then the disadvantage is that, as you can see, I didn't have control on individual coefficients, right? To for imposed congruence conditions. So to make the abelian variety ordinary, all I need to control is the congruence condition of the middle coefficient at p, right? But if I want to make sure my abelian variety is also geometrically simple and has a principally polarized isogeny one, you need to essentially control the congruence class of every coefficient. And that method didn't allow us to do that. And also the other thing is the obtained range for the order inside the Hasse Weil interval is not the optimal one. It's not the one that I showed you. So now let's introduce the second method, which helps with disadvantages, but on the other hand is more complicated and more difficult to be made effective. So namely, instead of starting from a power series with integral coefficient at truncate, what we'll do is we are going to start with a real polynomial with real coefficients and approximate it by an integral polynomial term by term, so that I will have better control on each of the individual coefficients. I'll do it step by step. Okay, so what we do is we take a polynomial with real coefficients. And another important thing here is that previously, when I took the power series and I truncate, you may notice that I truncated at degree n, right? My h had used to have degree n, and my targeting wave polynomial had degree 2n. Here, now, instead of h having degree n, we're going to take a real polynomial with degree is very close to 2n. So this gives us a lot more freedom, I think this is the major reason for this method to result a better bound inside the Hasse Weil interval, is we take a polynomial of almost degree 2n with real coefficients. And now we approximate it with integral polynomial term by term. So, and the polynomial we took is a very special form. We took a very low degree polynomial, which we called p, like the seed, and then take it to a higher power to be our starting polynomial h. Okay, and for our seed polynomial, this p, we ask it not only to not vanish in the small disk, we actually ask it to be slightly bigger than 0 inside there to give us more wiggle room later on. So what we did was we deform this h, starting h, which is given by p to the b, term by term, into a polynomial h, where this h, again, still have real coefficients. But when I take h hat has integral coefficients. So another realization is that all I need is for h of hat, which is my targeting wave polynomial, to have integral coefficients. But whether h had integral coefficients or not, I really don't care. All I care about is h hat. To satisfy the following 4 conditions, which are exactly the desired condition. So h of z does not vanish in the disk. H hat of 1 is the targeting number, and h hat of x is the integer polynomial. And moreover, it satisfies a congruence condition at all, mod L. Okay, so how we did that was the following. So we started with a polynomial satisfying 1 and 2. As you can see, I picked my p so that when I take my starting polynomial h, p to the b, the first two conditions are already satisfied, right? And all I want to do is to adjust to make the last two conditions satisfy. So what we do is so what we do is we will adjust one coefficient each time to make the conditions 3 and 4 satisfy for that particular coefficient or any coefficient before that. But then it will break condition 1 and 2, right? Then we will add another term to recover the condition 1 and 2, but didn't change the previous coefficients, and so on and so on. So it's an inductive way to do this. Okay, and this method gives us the better bound. Gives us the beginning, the much bigger interval inside the Hasse Weil interval. But again, as you can see, that because it's complicated, so it's more difficult to make it effective, and we didn't actually work out the exact bound. Okay, so in the last slide, I want to show you that we actually plotted consider the field F9 and consider all the Abelian surfaces defined over F9. We actually plotted how many F9 points it can have. Okay, so the horizontal row is the number of points, and if I have a Abelian surface, then its wave polynomial is a degree 4 monic degree 4 polynomial with integer coefficients determined by two constants C1 and C2, right? And then the point is that the main term for here, because I care about the number of rational points, means I care about the evaluation of this polynomial at x equal to 1. So as you can see, the main term here is really C1 because you have a 9 times C1 times x, right? So how many points the Abelian surface have really determines on what is our C1 value. And the C1 value is between -12 to 12. So the vertical line is the C1 value for each of the isogeny classes. And what I want to show you is that you see there are gaps. You see there are you can see that this is all the possible numbers for the Abelian surface to have. And then in between there are gaps, right? There are some points which does not occur. And essentially the reason is because C1 is an integer. And when you change C1 by C1 plus 1, it creates a gap. And this is why, and this is behind the work on the large Q limit, because the fact that C1 is the main term is because you see that you have Q times C1 x, and when Q to the, I guess, n minus 1. But when Q gets really large, when you change C1 to C1 plus 1, you create very large gaps between integers that you just could not achieve. Yeah, that's all I want to talk about. Happy birthday, Andrew. Thank you.
Are there any questions?
Yes, I think, yeah, there is work on which groups show up. And I remember that cyclic groups always show up, and many of them, okay, yeah. I'm happy to talk after, yeah. Let's see, I haven't worked on it, okay. Okay, I'm happy to chat afterwards.
Are there other questions? Okay, well, let's thank Wanlin again.